For the introduction. Reinforcement learning for finance. This is all based what we are going to do, or at least what I've planned for today, based on my new book for O'Reilly. It will be my 5th one. Before we get started, just out of interest and curiosity, who's working with reinforcement learning, generally speaking, algorithms related to it, is using it? Just a few. Who has a finance background, works in finance? Just a few hands. So there are a few here in the room who usually do not use, obviously, reinforcement learning, nor are from the finance field. So I hope there is quite a bit of new stuff that you will encounter today. I prepared a slide deck, and you see, it's difficult to see because everything is pretty small here, right? The slide deck is online, and all the resources that I'm going to use are online as well. So I don't know, you can follow along if you like to later on, or you just lean back, have a look at what I'm doing, and you can then afterwards visit the code and the Jupyter notebooks that I have already put online. So a quick, let me activate this here, quick introduction. So I was saying I was just finishing my 5th book for O'Reilly. Here you see the 4 and the 2 that I've published with Wiley. The Python for Finance one was the first, and it has, in the first edition, it has 10-year anniversary this year, so 2014. It's been a while since I've been writing, so started in 2013, writing the book Python for Finance in 2018. The second edition came out, and then later on the other books that you can see here. So this was really the starting point, and when people ask me, what are you doing, Eve, for a living? I said, it's Python for Finance. So it's my big business card. It has like 711 pages, that book. It's the thickest one I've written and published. All the other ones are related to other topics in finance. And in the book, for example, Artificial Intelligence in Finance, you find also reinforcement learning algorithms and a couple of applications in terms of algorithmic trading. There the focus is more on, in this regard, the deployment of such algorithms, really, in the context of real-time APIs, where such an agent is supposed, or a bot, as it's usually called then in this context, is supposed to trade on its own, which is for many people kind of, the holy grail to say, well, I have something here, an agent, I have a bot, and the bot is trading 24/7 maybe, for example, in the crypto markets on its own, and hopefully it might make a little bit of money. But to say this up front, although the topic is finance, no investment advice or anything like this is intended here. It's all about the technology and the algorithmic side here in this context. What I make for a living beyond writing books is the certificate in Python for Finance, which we offer since quite a few years now, and which has grown over time. I like to say that it's roughly like a master's program. Finance, so many resources you will find. People who do the CPF, they are not supposed to go through basically everything that we offer. Most do not do it. Most people cannot do it due to time constraints because they have maybe a day job, maybe they have families, maybe they even have a couple of hobbies. But anyways, they have indefinite access to the resources. So many people study with us over years and are eager to learn stuff that we put online, maybe even a year or two after they have finished the program. We also run a community, Quant Staff. It's on Discord, so if you're interested maybe to exchange ideas or to get a feel of what is going on in the field. Also, people are looking for jobs there, or people are offering jobs on the Discord server. So the community now has 1,000+ members, and it's still growing, right? In this context, I also made, this is related to what we are going to do today, I also did a webinar series about reinforcement learning and finance, which is to be found on our YouTube channel. We also run meetups here in London. We have the biggest meetup with some 3,500 members, or maybe close to 4,000 these days. And this started also almost 10 years ago, not exactly, I think it was 2015 when we've had the first meetup. Of course, during the COVID period, we stopped doing live meetups, but after that, we resumed it, not with the same frequency as before, but we are now planning to get another view in the calendar. And the same holds true here for the New York group. Too long to be read here, just for you as reference if you're interested where I'm coming from and what I'm doing. So the overview of what I was planning for today, I said it already, it's based on the new book. So just on my way here to London, I was reviewing the copy edit, so it's really in the final stages now, where it's about the minute details of getting a book publication ready, right? So this will come out, I think, in print towards the end of October. So it's now really a tight timeline, and we are close to the finishing line. We can see it already. And I was planning for the following topics. So this is the overview of what you can find in the book. First part is about the basics, learning through interaction, what is deep Q learning, financial Q learning, and then data augmentation, about simulated data and generated data. And a few applications are to be found in the book, obviously, which are, as the title suggests, finance related, algo trading, also dynamic hedging, dynamic asset allocation, and the optimal execution of large block trades, as they are called. And I was planning for what you see here in italics and a little bit more gray than the white ones, but no need to go through everything, but these are at least the resources that you will find in the gist, for which I will share the link in a minute. All right, so that's the plan for today. And for example, in our program, which I mentioned before, we have had a long class with like 20 sessions where we went really deep with regard to all the single elements that you can see here. Today we have like 2 hours, so it will be more like a little bit more of a rough overview from a high level perspective, so we cannot go into every single detail. It's quite a bit of code, but you will have access to the code, so if you are then interested to play around with it, maybe to adjust it, maybe to use other data or whatever, this will all be possible afterwards. Do you have any questions or suggestions so far for what I've planned for today? It's quite a bit. In particular, when I remember like how many people are working with reinforcement learning and how many people have a background in finance. As I was saying before, there's maybe quite a bit of new stuff that you will find in the resources that I'm planning to go through. Right. So here is now the link, the short link. It's bit.ly ODSC _LDN _2024. So if you go to that page, which I can do as well. So maybe this is my classes here. Bit.ly ODSC. Here we go. There is it already. Right.
Could you please display the link again?
Yeah. You see it here as well. So here you see it as well. I always put the link to the gist in the gist itself, so that you can always see it when I pull it up. So it's bit.ly /ODSC _LDN _2024. There, as the next link, you find the slides, the slide deck, which I was using before. And what you also find here, which I'm sharing usually not publicly, but I thought it would be nice that you get access to it. This is a preprint or an earlier version of the book in HTML form, right? So when you click on that and open it, this is not the format that you might be used to from the O'Reilly books, right? But this is the typical ASCII Doctor, as it's called, setting as an HTML. It's also, of course, fully searchable. Not the, as I was saying, the final edit, which we are currently working on, but it's a later version from August, before we went into copy edit. It has, beyond what I'm sharing with you in code form and what I was planning to do today, has basically all the resources, including, as usual with my books, all the codes that are self-contained and executable. And I always try to have the code in a reproducible fashion so that, for example, you can regenerate the images, the figures that you find in the book, etc. pp. Right? So that's about the resources, and you should have everything available online. I keep them all here pulled up that I can now get back. So everybody who wants to access it was able to do so. I hope at least. I think the Wi-Fi is working okay for our purposes here. So reinforcement learning, the resources are there, and I wasn't sure about that, but now that I've seen that not everybody has a background in reinforcement learning, has worked with these algorithms, I have included here in the slide deck a couple of basic slides, right, explaining what this all is about, what reinforcement learning is about, where it's coming from, and why it can be applied to so many problems in finance, right? So maybe a quick run through. This won't replace, I would say, a thorough study of the books that I show later on, but at least we might be getting a high-level overview, which might be helpful when we see the code later on as a background to better understand it. So dynamic programming. This has nothing to do with Python programming or programming language. This is a term for problems that show certain characteristics, and in finance we are faced with many such problems, right? There are famous and widely used theories which would be called static, right? Where you say, well, we are today here and now we have a look at tomorrow or at the end of the month or at the end of a year, right? So we have just like 2 points in time that are relevant. These are static problems. You say, well, I need to decide today, for example, to maximize a return towards the end of the year, for example, given certain criteria. But reality usually looks a little bit different, right? You need to make decisions dynamically, as it's called, over time, and you need to revisit decisions over and over again, right? It's like every morning when you get up, you need to decide what clothes you wear, right? A blue shirt, a white shirt, or whatever, right? And that's the same in finance. We have many, many problems like asset allocation when you want to invest in the markets that are in nature dynamic, so you revisit the decision in regular intervals, whatever the interval is. So for us later on, this won't be the major point, but you can think of it like on a daily basis, on a monthly basis. Some things are done quarterly, right? But it has the feature that it's in a more or less regular fashion. And the left-hand side, that's a general book about optimization theory, and you find there in a, I think, pretty good introductory way the basics about dynamic programming. And for those who might want to go deeper, the right-hand side book that's really involved in terms of mathematics. This is a whole book about dynamic programming, also involving the, I would say, high-level mathematical machinery to attack problems, for example, that are placed in a continuous time context. But for us, that's not really relevant, because whenever we do some programming, usually we are talking about discrete time steps and discrete state spaces. But all these technical terms that are not really relevant for what we are later on see in a very practical manner, right? But just to have a little bit of formalism here, such a dynamic programming problem, which might be Markovian with a finite horizon, which means, well, we look forward maybe 10 years or whatnot, is characterized by a certain set of objects, right? S is the state space, and A is the action space, T is the time horizon, and then we have for each point in time, this is what I meant before in terms of like dynamic, right? We have multiple points or many, many points in time at which a certain decision is to be made. Whenever the agent takes an action given a state, there is a reward that is attached. So a canonical example is, for example, a game, right? It's card games. Think of it in terms maybe of an Atari game, or you can put this in the context of a board game like chess, right? And the state space, for example, in the chess context would be the board position, right? This is what the two players see, and player one can take an action, so playing the white pieces, and player two then in turn takes an action, playing the black pieces, and so forth, right? And then we have a transition function from a state taking an action to another state, right? When a piece is moved, the state itself, the board position overall changes. So this is a bit formalism, but again, I don't think that this is really necessary to understand what's coming later on in terms of the practical applications, but this is the background based on which everything else that follows can be seen. And one important element is that there is usually some objective function which is to be maximized, right? When you play a game of chess, you want to win, right? You want to put your opponent checkmate. When you play in a card game, you may strive to get the high score, right? When I was young playing the card games, right, we were always eager to, stay on top in the rankings to maximize the score. So based on the actions taken. In finance, this might be investment decisions taken over time to maximize the profit or to maximize the return in that context, right? So some basic notions after this formalism so that we have at least a good grasp what we are talking about. Now here in this context, as a background, I said we cannot replace a thorough study of this book, for example, which is the standard reference work, right? I don't want to go into details here, but for those of you who are interested, this book is also available online as PDF, so officially available online as PDF for download, and it's a standard reference. Doesn't have code, but it gives you the basic algorithms, the basic ideas, the motivations, the mathematical aspects of what we are talking about. So, and it's also pretty well written. I like the book quite a bit, right? Just as a background, right? Reinforcement learning, when we want to have a higher level perspective and how it relates to other machine learning methods, we know there is something that is called unsupervised learning, there's something that is called supervised learning, but when we think it through, the reinforcement learning idea and approach is that which is usually from our human experience, the most natural one, right? So we human beings do something, we get feedback, we get better at what we do. Think, for example, playing tennis or playing golf or again, playing chess, for example. You do it, you try something out, you get feedback, you improve what you do. And this is actually here in these books, it's explained, not exactly against the background of reinforcement learning, but this is, if you like, the philosophical framework, the science of consequences and a book of why, which plays a major role around reinforcement learning and why this is kind of like a pretty good approach and why so many great breakthroughs in the field have been achieved by reinforcement learning and not necessarily by the other methods that I mentioned before. So we all know about the success stories with regard to playing the game of Go and chess and AlphaGo, AlphaZero, and all these stories that are well documented also in the form, for example, of a full feature movie that is available on YouTube. So with regard to the basic notions now, getting a little bit more formal, but I think that's the level that is good for what we are going to do afterwards. The environment is, in abstract terms, what defines the problem at hand, right? So this can be, again, a game environment, like for a board game, or it is a financial environment, what we are dealing with, right, in terms of the investment problem or the hedging problem or whatever the financial problem is, right? And then we have the state, which describes the environment at a certain point in time, right? So this is usually done by a small set. Usually you want to choose it as small as possible of relevant parameters, right? And the agent can observe the current state. Again, in chess it would be the board position, and in a card game would be the screen, or in the financial world, this would be information about the financial market, like what is the index level, what are short rates, what are other indicators and numbers, generally speaking, that are relevant to my decision problem that I need to take into account in order to take an action, or in other words, to make a decision. right? So environment plus the state describing the environment, and the agent itself, this is what, in the real world might be some human being, right? But for us, this will be a piece of software, and this piece of software will interact with another piece of software which represents the environment, right? So we have the agent, right, which observes the state of the environment, and based on the state, the agent has either just a few possible actions that the agent can take, or maybe an unlimited set of possible actions. We would then speak of a control problem, right? In a gaming context, this might just be move something to the left, move something to the right, or jump, or whatever, right? So in a financial context, this might be I invest 50% in a stock, or I invest 60% in a stock, or just 20% in a stock. That's then in a financial context, and where we're saying this can be an unlimited set. In many introductory examples, this will be just a limited set, for example, 2 possible actions or maybe 10 possible actions from which to choose the maximizing one, the optimal one. So that's what is described down there. The action, again, this can be just a movement to the left or to the right, or we have in financial markets to go long in an investment or to go short. So this is defined by the problem at hand. So we cannot say this is always the case that we see X, Y, that. This is to be defined by the problem that we are faced with. Then we have the notion of a step, right? We have an environment, we have the state of the environment, an action is taken, and step is, so to say, the notion of going from one state of the environment to another state, given a certain action of the agent. Right? So that's generally enough to encompass different time intervals, for example. So when we speak of a step, there is no real fixed time interval attached to it. I said before, this can be 1 day, or this can be a month, it can be a week, it can be in years, or it can be heterogeneous, that we say sometimes it's every day, sometimes it's weekly, so this might change as well. Obviously, when we are dealing with APIs and software, it will be faster than what we human beings would do, right? When you think in terms of playing the game of chess, you might have an average of 3 minutes per move, but the agent here, the AI, so to say, the bot is able to maybe make 1,000 moves per second, for example, right? So therefore, this might change also with the application. And there is a reward attached to it. That's the feedback, right? You might recall the book cover from before. There are consequences attached to an action, and that's the reward. This can also be a penalty, right? If something is good, you might get a higher reward, or if something is done wrong or not so good, there might also be a penalty. Often I would say you either work with reward or penalties, but there might also be situations where this is mixed up. Again, this depends on the problem at hand, and often this is really like, I would say, the hard part, maybe the art in this context, and not necessarily science to get the reward defined in a way that the agent learns the problem at hand in an efficient manner, right? And there's a target, that's the objective, right? A high score, or to minimize the penalty, or whatever this might be, right? In finance, we would usually say, well, to maximize profit or to maximize the return. That's basically the standard target, I would say. Then the policy, this is what the agent tries to optimize over time. So when presented with the state of the environment, the agent in the policy, so to say, defines what action it will take, right? So later on, when we talk about Q learning, this is then the embodied by the Q in Q learning, which is the abbreviation usually for the policy at hand. And an episode is like one game, let's say, right? Like one chess game, or it's like one investment period. So from start to finish, and the agent is supposed to go through many, many episodes. This can be Many can mean maybe 100, or many can mean 10,000s or millions of episodes, meaning games played, for example. So deep Q learning now is a special form of the algorithm, right? We have the reward function here. It's now a bit formalized, right? We have the state given and the action taken, and this gives a reward. It's a number. Can be positive, can be negative. Positive, you would say that's a reward in its original meaning. A negative number might then be interpreted as a penalty, for example, right? And the action policy, this is the Q that I was referring to, right? The action policy assigns to every action given a certain state also a number. So these two numbers are different, right? The reward is one thing, and the value that the agent attaches to an action and a state, it could be the same, but usually it's different. And here we see one important element. Q learning rests on the combination of the immediate reward and the delayed future reward. So it's looking forward always one step. So it's not saying, well, give me everything now. No, the agent is supposed to look forward and to, so to say, simulate what is the reward when in the future, in the next step, I take an optimal action. And since this is like always looking forward at every step over the episodes, this connects all the steps with each other, and based on certain mathematical principles like the Bellman principle, Bellman equation. This makes sure this formulation makes sure that the agent will achieve, at least in approximate terms, an optimal strategy, an optimal maximal outcome, right? So why deep Q learning? Yeah, we are using here deep neural networks to represent the policy, because usually we cannot write it out, right? We cannot say, well, we have just 5 states and then we have for each state exactly defined what the optimal policy is. So just think in terms of chess, right? We have as many board positions that are possible as we have atoms in the universe, so we cannot write this out. It's well too large. So we need to have some approximation. We know that deep, dense neural networks, in our case, are pretty good at approximating such phenomena, let's say, the policy here, which is a bit abstract, but which will be made concrete by the use of the DNN. When I say we cannot write it out explicitly, for example, there are situations or contexts where we could write it out. Think in terms of the game tic-tac-toe, which pretty simple, everybody can play it, even small children can play tic-tac-toe, and there are just a few possible, or relatively few, possible states of the 3x3 board, so to say, and this is something that you could really write out, let's say in an Excel spreadsheet, for example. But again, for chess, that's impossible, and for most other situations, that's impossible as well. Therefore, neural networks come to the rescue, and we can use it to get good approximations for the optimal policy. Here, just a link to some mathematical proofs in this context. So 2 notions are important in this context here. When I speak about an optimal policy, this does not mean that the agent always behaves optimal. In the beginning, the agent might not know anything, right? He might not have a clue what might be optimal at all. So what the agent is supposed to do in the beginning is to explore, right? And by explore is meant that given a certain state, the agent knows at least what type of action or what action it can choose, and it will explore in a random fashion different actions, right? Because it might not know, and usually the agent does not know, given a certain state, what an optimal action might be. Therefore, it might, given one state, when presented with this one state, might explore different options, different actions, and over time will learn things, right? I mean, just think again in terms of a chessboard. When you get started, you have multiple options for the first move, right? You can move one pawn or the other pawn, right? There might be better ones and worse ones. There might be ones that are on equal footing, right? But when you get started, you might explore different things there, right? And later on, that's supposed to diminish over time, the exploration part, and the exploitation part is supposed to increase over time. Later on, the agent will rely more and more on what it has learned, and in that sense, on the optimal policy. But I think it makes sense that this is something for later, right? Because in the beginning, first exploration, just checking out things, and later on relying on what has been learned. And when I speak of learned, replay here is the expression or the notion, right, that the agent regularly updates what it has learned in terms of like looking back at past experiences, and based on the past experiences, updating the policy, and later on relying on what it has learned. I think when you think it through, this is all pretty natural. I would say this is how we human beings behave as well, right? We go through life, we make experiences, and maybe in a quiet moment we reflect on what was happening, and we might update our internal policy, which might be pretty abstract in our real neural network in the brain, right? But this is how we learn, and for example, how animals learn as well, right? They try out things and they get feedback, and they adjust their policy, which sounds a little bit abstract, but I think we can relate to it when we think it through. And then there are a couple of technical parameters. Gamma is the discount factor, epsilon is the parameter which defines the ratio with which the algorithm relies on exploration as compared to exploitation. And I said this changes over time, and this is what epsilon decay brings in it. So that much about the background. Are there questions? None at all. It's all new or all? Yeah, there's a question.
Question here. The agent is obviously holding a portfolio of stocks and markets, right?
For example, yeah.
For example.
Yeah.
Now, is that part of the state of the environment as well, or is that a separate kind of state of the agent? How does that work?
Yeah, it depends on what you want to model, right? So I have a couple of examples where I can exactly show how the state is modeled in this context. So generally speaking, I wouldn't say one or the other is correct or incorrect, right? It always depends on what is really the problem at hand and what do you want to learn or want the agent be learning, right? And this usually then defines how you go about it. So for example, I would say when you're just in simple terms, for example, just a universe of 3 stocks, right? When you have 3 stocks, that's already kind of like a typical problem, I would say, in finance. And the state of the environment, for example, can include the prices at a certain point in time of these 3 stocks. And given the prices that the agent then can observe, because it's part of the state, the agent might shift the portfolio composition one way or the other, right? Might increase the allocation of one asset and at the same time decrease the allocation to other assets and so forth. Right?
Right. Yeah, because I'm just saying that the policy, based on the state you're saying, defines what action to take.
Exactly.
In this case, it's the state is the environment as well as my holding currently, right? So is the state defined by both or one, I guess, is what I was trying to get.
Yeah, again, when you say, I was saying, well, the stock prices might be part of the state of the environment, right? This is something that the agent can observe, but usually cannot influence in this context, right? But there might also be parts of the state description which is related to the allocations to the 3 assets in my example, right? But this is then also part of the action, right? The action in this context would be, and this is one example that we can go through, right? The agent would then decide what is the allocation to the 3 assets, right? Therefore, in that sense, I have it in the state modeling included because I use it then for the optimization, but this is nothing basically what the agent would use to make a decision, right? The decision is made based on the prices, right? But then the agent decides, okay, I put 20% in the one thing, 30 in the second asset, and 50% in the other one. So this can be part of it, but this won't influence directly in that sense the decision or the action that the agent will take. Right?
So
But changing prices, this will influence the.
so it's the change in the portfolio that is what we are defining as the action, rather than selling something, because I can't sell what I don't own. That's where I think I was getting.
Exactly, yeah.
Thank you.
So the action might be 3 numbers, right? 3 numbers defining the allocation into the assets. Yeah.
Thank you.
Yeah. One after the other. Yeah.
In the example of chess,
Yeah.
what would the difference be between the reward function and the kind of delayed reward queue, or would they be the same thing in that problem?
Yeah, that's the typical thing. When you're playing chess in the beginning, you might be eager to capture pieces of your opponent, right? This might be the immediate reward. Oh, I got, I don't know, the whatever piece, right? I got it. But this might be bad for what is coming later on, right? You might tap in a trap, right? By the sacrifice of your opponent, right? And the immediate reward is, yeah, I get like, given the points usually attached to the single pieces, 3 points plus, 4 points plus, right? But you might lose the whole game if you capture it, right? So the delayed reward is what is happening afterwards. So I mean, everybody has heard it in the computer context as well as for human beings, right? Not a single player, not a single algorithm will just have a look at the next move, right? They will always look further and they say, well, grandmasters can look 18 moves ahead or whatnot, right? Machines for sure can, right? It of course depends on the number of pieces on the board, right? But in terms of end games, for example, this might be 20, 30 moves, right? In terms of like a strategy setting up. So the delayed reward is like always looking forward and not just focusing on what is in front of you, right? It's also like the immediate reward of eating 3 pieces of a cheesecake, right? Versus gaining weight, right? This might be then the penalty afterward, right? You might just go with one piece of cheesecake and benefit from it later on in terms of health and less weight gain, right? Yeah, we go over there and then, yeah.
Later, I think you're going into deep Q learning. What is it about, I guess, your problem space or your domain that makes that the choice for the algorithm? Is there something about financial problems that makes deep Q learning particularly applicable? Or?
Yeah, I said we don't need the formalism, but you might recall that I introduced dynamic programming, right? And finance overall is driven by dynamic problems, right? The prominence of static problems is like, I don't know, because they are simple and intuitively appealing, but the real world is not about static one-shot problems and solutions, right? So, and generally speaking, when you have dynamic programming, this usually involves heavy mathematical machinery, and depending on the problem, how it's formulated, you can come up with closed form analytical solutions, right? But there are also numerical methods that allow you to come up with an approximate solution, right? And reinforcement learning is one algorithm which allows you to solve dynamic programming problems approximately, right? Therefore, this as a numerical method is therefore so attractive because many problems in finance satisfy the definition that we have seen before, and you can apply reinforcement learning in the form of deep Q learning to exactly this type of problem, which you might not be able to solve, or most of the problems are not solvable in analytic fashion, right? So you need to resort to numerical approximate methods, and reinforcement learning has proven to be a pretty good method in this context. Yeah. 1, 2. Yeah.
If I understand this right, the reward function must be a proxy for the target.
Not necessarily a proxy, right? But yeah. I mean, you can have, if you say simply a P&L, if you say maximize the profit, right? This is not, I would say, a proxy. This is exactly what is happening maybe in the financial market, right? Here.
Does that have to be a distinction between the two?
Between?
Does that have to be a distinct? The two things have to be distinct.
What do you mean by the two? The target itself and the reward?
Itself and the reward.
No. I mean, the target usually, in my world, how I define the single expressions and notions is you have a reward and your target might be to maximize the total reward over all the steps per single episode, right? In the end, they are the same, right? If you have like, let's say, 12 trading decisions to be made over the course of a year, right? Then you can divide the year in 12 different rewards, right? But you might want to maximize the total reward of the 12 different profits. Hopefully not losses, but this cannot be avoided in the financial world, right? So overall, your net profit is what you would maximize. But this is then, again, the addition of certain single rewards or penalties, losses that you can book or need to observe. Yeah.
So I wanted to ask, is there a one-to-one mapping between RL theory and game theory, or does it like take some things from there and some things from other paradigms?
Yeah, in many contexts, you could come up with relationships, but the problems that I'm addressing, they are not necessarily based on game theory in the sense of having multiple parties that interact with each other, maybe under the condition of incomplete information, etc. Right? When you think in terms of, I don't know, chess is a game of complete information. The two players know exactly what is relevant, right? But the game of poker, for example, not. Therefore, in the game of poker, game theory in that sense plays a more important role. But the problems I'm addressing here that can be attacked or usually are addressed in a non-game theoretic manner, because we are just modeling usually an agent that interacts with the abstraction of a financial market, right? Not one trying to exploit the other, for example. But of course, there are so many examples in this regard as well. Yeah.
I was going to ask, so in a lot of the examples of RL, like games like tic-tac-toe and chess, there's a discrete number of actions the agent can take. How do you approach it in finance, where I could invest anything from like 0% to 100% of as a continuous spectrum of decisions? Or do you deliberately kind of restrict what the agent can do to make there less options?
Yeah, sometimes you would go and discretize your continuous space, right? When you say, my decision to be made is between 0 and 100%, right? You have an infinite number of options, right? You can have 54.77888897, right? How I do it here, I model it as indeed as an optimal control problem where I optimize over the number, right? So like a typical optimization problem, you say I want to minimize a function, I want to maximize a function. This is how I model it here in that context, right? But you can, as you're saying, you can discretize it and then have your limited number of actions to be taken, right? Where you have, for example, the mapping of the state space to, let's say, 10 different actions, right? In 10 percentage point steps. I do it differently usually here in terms of really modeling this as an optimal control and leaving it as it is in terms of an infinite number of options that the agent can choose from. Yeah.
Yes. Circling back to the reward question, I think reward shaping is a big challenge in reinforcement learning in general. So I just wanted to know more about that challenge from the perspective of finance, and maybe going back to maybe do we want to like get as close to like an actual performance metric to model the reward, or what kind of challenges like do we have?
Yeah, I mean, I would say often in finance it's pretty clear, right? Finance is about optimization, generally speaking, right? You want to maximize your profit, you want to minimize the risk. You want to, it's always in the wording, in the problem formulation itself. But this doesn't necessarily mean that the reward function or how you define the reward and what the agent is doing with it is always pretty clear, right? For example, when we say we want to maximize, let's say, the Sharpe ratio, which is the return over the risk, right? So risk-adjusted return, right? This might be the target, but you might have other elements that might be of importance, right? What I do, for example, I have Sharpe ratio as my target, but for example, I penalize changes in the portfolio composition, because you don't want to have that the agent has 100% in one asset and 100% on the next day in the other one, right? You want to have something more stable over time. Therefore, for example, this is in terms of the reward, I add some penalty for certain actions in this context. But again, this is all to be defined, all to be figured out once you have the problem specified and you say, well, this is my target, but these are, for example, other constraints that I want to have included in it. But often, again, I say, well, maximize the return or maximize the Sharpe ratio, minimize the risk, or when we talk about dynamic hedging, right, get the payoff of the portfolio as exact as possible, right? This would then be the derivation, right? You want to minimize the absolute derivation from a certain target quantity. So in finance, I would say it's often pretty clear, but of course there are minute details which might play an important role and which might make the agent learn a bit more efficiently or a bit more slowly, depending on how you define it, how you scale it, and yeah. I don't say that's simple. Of course, there's a little bit of art, but we have the financial science, quote unquote, which often gives us a good guideline with regard to how to formulate these things. Right? Another question, yeah?
So in reinforcement learning, sometimes you have to do like evaluations offline to determine how good is your model before you put it into production. How do you deal with situations where you don't always have historical data on state, on the state that you'd expect when you're trying to, like essentially off-policy evaluation of your model? How does that work?
I mean, you might recall when I was showing the overview, I might be getting back to it. That would be a good point. Right, data obviously is a problem in all these contexts. We have the luxury with regard to, again, my standard example, the game of chess, right? You can have the engine, the agent, play as many games as are required to reach whatever level, right? So, but in finance, we usually don't have it, right? We have much, much more data these days than they have been around in the 50s, 60s, 70s, when all these quant finance theories have been developed, right, for asset allocation, etc. Back in the days, they just had end-of-day data, sometimes for maybe a year, sometimes for maybe a few years, right? And they applied their regression, right? When people ask, why is there so much ordinarily stress regression in finance? Yeah, back in the days, there were no computers around, right? And this was what the assistants of the professors could do with pen and paper, right? So data obviously is a problem. And still, although we have a ton of data available these days, it might not be enough, because when you have a look, also one of my standard examples, at historical end-of-day data for Apple, right? Apple went public 1980, so let's assume this is roughly 40 years or now 45 years soon. You have 252 trading days, so per year in 10 years, it's 2,500 data points, right? In 40 years, you have roughly 10,000 data points. Let's assume we now have 12,500 or whatever, sometime soon. But this is not a lot of data, right? 12,000 data points, right? And it is this one time series that you've got, right? And you can go over and over the same time series. What we all know, this will lead to in-sample bias, to overfitting, to whatever. And it might in particular not be enough to train an agent in a manner that what you're saying is, in finance we would say that it performs well out of sample, right? That has seen maybe a few data points, and now we expect it in the future to, I don't know, by algorithmically trading, going long and short, whatever, to generate decent profits. So that's of course a problem. Therefore here the second part of the book deals with data augmentation. Traditionally in finance, in this context, we relied on Monte Carlo simulation. This is used in many different contexts for pricing of options, for risk management purposes, and so forth. So this is, I would say, well established, but it's always a simplified model of reality, meaning of the stochastic nature of prices that is used as the driving force behind the data generation, right? And this is then the point, and I've planned to show you this as well here, but we are already progressing pretty fast here in terms of the time, to use generative adversarial networks to generate synthetic data sets which are statistically indistinguishable from the original data set. So when we have a look at the time series, I'm not talking about prices here, but rather about returns, which is usually what is getting modeled, that you can generate return-based time series data, which is statistically the same, quote unquote. So given certain tests, it's indistinguishable from the original one. So this is one approach, and I find this pretty appealing because you can indeed then generate as many time series, like playing as many games of chess as are required, right, to reach a certain level. This still doesn't give you a guarantee, because this is in finance always about the future, but you might nevertheless improve your algorithms, your agent by quite a bit. Good. So maybe let me pull up, and I didn't check with regard to the gist. I have the, oh, I don't have the Jupyter notebooks yet in there. Let me just check. Completely different. So here, yeah. So let me push now the Jupyter notebooks as well to the gist. Need to reload it. No, we might. Here we go. So it took a while. Now when you're on the gist page and you refresh it, you will now see the Jupyter notebooks, right? The 5 that I mentioned. And you see here, this is not necessarily now numbered. When you see here chapter 1 and chapter 3, this just means that I left out the Jupyter notebook, which was the basis for chapter 2 in the book, right? So when I open out the first one, and this is not yet about reinforcement learning, but this is an example that I like to start with, because it, in the end, I think illustrates pretty well how overall, generally speaking, reinforcement learning, and in particular in the form of deep Q learning, works, right? When you go to the text, you can read the explanation. This is here about a game of coin flipping, right? And usually would say when you predict heads or tails correctly, you might win $1 or €1 or £1, right? And otherwise nothing. So you don't need to bet, but this is the basic idea here. And I'm using here already a few notions. Right here, SSP is meant to be the state space, right? We can have heads or tail. Heads would be 1, tail would be 0, and we have the action space, which here coincides with the state space, right? When I'm betting on the coin flipping game, I can say, yeah, I think now heads, right, will be the next outcome. Or tails, right? These are the two options. And here we have one epoch or episode, as we have called it before, where now in this context, the agent takes a random action. So this would be the exploration from before. The agent doesn't know anything, right? And when we are dealing here with a fair coin, fair game, right, there is nothing to be known, right? So the agent chooses an action randomly, then the coin is flipped, and if the prediction was correct, then the total return is increased by 1. So for every prediction, I get a reward of 1. So +1 when I'm correct, 0 otherwise. Right. So now I play 250 epochs here, right? And with my uninformed betting here, just taking random action, we get here different results, like 56, 47, 48, 50. So on average, like this is the situation playing roulette, black or red, right? On average, we would expect here an outcome of 50, right? Because it's supposed to be a fair game, and it's programmed here to be a fair game. So the average here is pretty close to 50. When you go to the casino, sometimes you might be lucky, 55, and you think, oh, I got an edge, right? But sometimes you might then return and think, oh, I got this huge edge, and you are losing here on average quite a bit, right? So now we turn our attention to something that is not a fair game anymore, right? So here you see the state space is now different, right? We have 4 times 1 and just 1 times 0. The action space play remains the same, so I can bet on heads or tail, but what the agent might not know, right, up front, that the game is rigged, or we have here a biased coin, so to say, because when the code remains the same, we will see on average 4 times as many 1s than we will see a 0 in this context, right? So when the agent now plays the same strategy, just randomly choosing 1 or 0, we are still getting the same outcome, right? This might not be intuitive, but since here the agent is using this uninformed strategy, right, we get the same outcome. So even if the game is rigged, if you are playing in a random fashion, you get the same return as before, right? So that's the one insight. Now, let us do something else. Now let us have the agent learn from past experiences, right? So you see, I try to build the bridge to the reinforcement learning world, to the deep Q learning algorithm. The game is biased, or the coin is biased, the game is rigged as before. 4 times 1, just 1 times 0. The action space here starts at 0 and 1 as before, but this time around, the agent recalls the experiences. Right? So I append like everything that was happening in the past, and the strategy remains the same, just randomly choosing from the ASP list object, but the ASP list object will be changed over time. So it will include all the past outcomes. Right? So this is now supposed to be a certain form of learning. Right? I recall what was happening before, and this is something that is pretty natural, right? Here, this now gives me a better outcome, right? I can now benefit from what I have observed in the past, and I play based on what I've observed in the past, now what is called a probability matching strategy, right? When we see here some 4 to 1, this means probability matching. In the end, when I play enough games, I know that 1 or heads is 80% of the time to be observed, and the 0 tails just 20% of the time. So with this strategy, I benefit here. Instead of just 50 as the expected reward, the average reward, I'm getting 66.78. And again, this is natural for many human beings as well as for animals. In the book, I'm citing sources in this regard. Probability matching has proven from an evolutionary point of view to be a good strategy for populations of birds, and several examples that I mentioned in the sources. But it's not the optimal strategy here, right? What I'm doing. What would be the optimal strategy?
Always 1.
From a certain point on, once you recognize it, you see, right, that 1 is much more often to be observed, we would just bet on 1, right? Why should you go with a 0 when 80% of the time, you know, the 1 is showing up, heads is showing up, right? Therefore, this is not optimal. It improves upon the uninformed strategy, right, by learning and remembering. Again, this is to be observed in the real world in many different contexts as well, but it's not here from a learning point of view the optimal strategy, right? Here, the code now is changed as follows. I also append past experiences, what was observed, right? But now I start just here using the most common one that is observed, right? Here's a very simple context, but could also be that we have, instead of just 0 and 1, we might have 0 to 100, for example, right? So the most common one, which means, or which was already pointed out correctly before, the best strategy here would be to then bet, once we recognize what is going on and which way the coin is biased, the game is rigged, right, to just bet on one. And what we then get here are much higher numbers once again. So here it's not exactly 80%, but close to 80% is what we get, right? And this is basically also the mechanism that the reinforcement learning agent will do in a more sophisticated manner, right? I was talking about deep neural networks and maybe infinitely large state spaces, etc. But in the end, this will be similar to what we see here, right? The agent is doing first some random stuff, right? Doesn't know anything, that's the exploration. Then over time it learns, it observes, right? It also recognizes, memorizes past experiences, and based on the past experiences, the policy will be updated so that in the end the agent knows what to do best. Here it's of course a very simple context, but the basic idea I think is pretty well illustrated here, right? And this is what we see here. This is what is called Bayesian updating, right? So after you have your prior, right, you might not know anything. You would assume you have 50-50, maybe in the beginning without having observed anything. Then you move forward, you play a couple of games, and from a certain point in time, you update your prior beliefs. You have your posterior, and you would say, yeah, I've observed 80%, 20% over time, so I'm going to bet just on heads in this context. The same holds true when we translate this to other contexts here. Another very simple example. I go through this quickly now. You see here a die, right, where 4 is more likely than all the other numbers for a 6-sided die, right? When I simply play in an uninformed manner here, 600 times, so the 100 here now needs to be seen against the 600 rounds that I'm playing here, I get an average of roughly 100, right? So here I have the probability matching strategy, everything else being equal. And we already see a major increase here to 176 instead of just 100 on average. This improves it, but we have learned it before. This might not be the optimal strategy, right? We just go now and play again the most common one. And here most common is a bit more meaningful than before, where we just had 0 and 1. Now we have like 1, 2, 3, 4, 5, 6, right? But it chooses now just 4. And this means that we are getting here 300 because this is like our 50% winning probability in this context, right? Yeah, and then there's just a calculation which I used to then illustrate and to say, well, that certain contexts are so complex that we cannot go, cannot attack the problems in the same simple manner that we have been doing it before. We might need other techniques and again, maybe some deep neural networks to approximate an optimal function. So after this simple example, now I think we have the basic notions. We've seen how Bayesian updating works, and I was saying that a reinforcement learning agent will behave similarly, right? In the beginning, just randomly choosing certain actions, memorizing the experiences in terms of the reward, and later on then relying on what the optimal policy says. Here in this context would be just bet on 4, before it was just bet on 1, right? And this is similar to what the agent would do in a reinforcement learning context, right? So, speaking of the agent, let us have a look at the finance world here. And first, obviously, at the finance environment, because without the environment, the agent cannot do anything. Our environment, we learned, it's in abstract terms what the problem is all about, and it is the abstract object based on which the agent can interact and can learn by receiving feedback, memorizing it, updating the policy, and all the elements that we have discussed before. Maybe I go through this also step by step. Right, a couple of imports and some technical elements here with regard to making the API in line with what the Gymnasium environment originally developed and maintained by OpenAI. This is now put on a different footing with regard to different team that maintains it. So here, action space sample, this is what we would call exploration, where we, as before, just take random actions. 0 or 1, 0 or 1. Like we did before. That's the very same thing, and here just illustrated based on 10 random actions chosen, and you see here this is a simple thing just to select from 0 and 1 an action. Right. So now to the environment. So the environment is based on a fixed data set. So there was a question about data, in sample, out of sample. How can we go about it? So the first examples in the book are based on a fixed data set. I use this throughout the book, this data set, but later on I also use simulation approaches and different things, right? But here first, to get started with, just the historical time series, right? Where a symbol needs to be defined, the feature needs to be specified, the number of features that we've got, action space, a minimum accuracy, which is by default here set to 48.5%. And a few more things. You see here the data is retrieved. Again, I try not to get into every single detail here. Most of the code, in particular, since you have access to the preprint of the book as well. Whenever you see here a call out, every single line is explained in the book. Maybe I show it here once, right? The book here, this would be the finance environment, chapter 3, right? This is the code that you have seen before. And when I'm speaking here of call outs, you see that every single line is explained in the text. I hope at a sufficient level in terms of details, right? So therefore, I think it's justified that I go through it a little bit faster here. Right? So that's the starting point. Once we have the data is prepared, right? You see here that I derive log returns from the data, and I derive directional data here based on the sign of the return. And here there's also another data set created where I normalize the original data in Gaussian fashion. Right? So I subtract the mean and I divide by the standard deviation, meaning we end up with a data set where the first moment is 0, so the expected, the average value, and the second moment, the standard deviation is 1. This doesn't make it normal. You might know when you've worked with financial data, you are usually not faced with normal returns, although many financial models assume that, but real-world data usually is everything but normal. Right? But at least we have here a normalization with regard to the first and the second moment. Then I reset here the environment. This is always the starting point, right? When I push the reset button, the environment is set to the starting point. Again, the context of chess, like the original starting board position is like recreated so that a new game can be started and played. So I might want to execute that code so that we see it later on. So then we come to the step. We discussed step in abstract fashion. Here you see it programmed out. Right? There is the step method, which takes the action as input. So here we allow for 2 actions, and the game is about predicting the next day's movement. Right? So the agent is supposed to learn what the next day's directional movement will be. So we simplify this to up or down, whether the market moves up or the market moves down. In a financial context, when I'm a trader and I'm good at playing this game, I might have a good chance to become rich, right? It might be nice to know how large the up movement might be or how large the downwards movement, the negative return might be, but if I'm already in a position to somehow correctly predict, let's say 55%, 60%, whatever, to predict the next day's direction of the movement, of the return, then this is already a pretty good thing to know, to have learned, and to be able to do, right? And you see here, I said correct to true when the prediction is correct and otherwise to false. And here I've written it out. This could be done much more compact, but I thought for the beginning this is a little bit more expressive. And the reward is 1 if the agent makes a correct prediction and otherwise 0. That's again the same as the simple example with the coin tossing, the coin flipping game, and the example with rolling dice, right? So if I'm correct, I get a reward, otherwise I don't get anything, right? The total reward here is updated by reward. The environment is moved 1 forward, so I use here a typical financial term, bar, right, which just says we are at position 100, 101, 102, 103, right? So moving forward in time. The accuracy is calculated, and only here it now might make sense what was defined before in terms of the minimum accuracy, because I'm defining here, so to say, a break condition, and first I check here whether we have exhausted the data set, right? Once we have reached the end of the data set, nothing can happen afterwards. Right? If this is not the case, and the reward here is set to 1, it's not finished. And here, this is the breaking condition that I mentioned before. So I require here for the agent a minimum accuracy that I can define. In the default case, it's 48.5%. This is just meant to stop early in cases where the agent simply doesn't do any good, right? To be below or well below 50% is simply nothing where you might want to continue. But this is for the learning, right? Later on for the testing, for example, you could do it differently. But I also give it a grace period, right? So I don't want to stop it out early when after 2 or 3 predictions it's already below that, right? So I wait for 15 predictions before I check for the accuracy. And then I return the next state, the reward, whether it's done or not. And this fixed false, it's just to be in line with the conventions of the gymnasium environment. So I instantiate this object, right? And in the data set, I have the following symbols: Apple, Microsoft, Intel, Amazon, Goldman Sachs, the S&P 500, the VIX volatility index, the SPY ETF on the S&P 500, euro US dollar exchange rate, the gold quote, gold index, and 2 gold ETFs. For what we are going to do is not really relevant with which we are going to work, right? But this at least is the set of options, the menu of options that we can use here instead of euro US dollar. So you can play around maybe with others there. So when I call reset to get started, you see we get the state of the environment in terms of 4 numbers, 4 floating point numbers. This describes the state of the environment. These are the first 4 normalized price data points in this context. Here you see the symbol was chosen euro US dollar, and the feature here is euro US dollar. Alternatively, I could go with R. I think I do it. Yeah, I do it exactly. So I wanted to do it here. This is something I show here. When I now get a random action, I can step the environment forward. And when you have a look here, this was the second data point. This becomes the first. This was the third. This becomes the second. So we move over the time series forward here, step by step and action by action. If I define the feature to be the log return, I get different numbers here, also normalized as we have seen before, but of course different values. So we have basically these 2 options for the feature. Either we work with 4 lags of the price data, normalized price data, or we work with 4 lags of the normalized returns. So now the agent. The first agent, here it's just the random player, the random agent, which, here we have it, doesn't have something like a deep neural network for the optimal policy, right? It simply takes random actions, right? And I can instantiate such a random agent and can let it play a couple of times, and you see the reward here is not that large because after a certain point in time it will drop below the minimum accuracy that is required. So it will stop usually early. Maybe the agent is lucky, like here 31. We can play it again. Right. So here 56. This seems to be like a lucky punch, but usually there will be just a few predictions here and a few rewards before the agent drops below the minimum accuracy level, right? So we just have here an average in the second round of 22.78. Right? So now to the real agent. For the first time, a couple of imports. I worked throughout the book with TensorFlow, no PyTorch, but I was thinking maybe once the book is finished to maybe translate the code to PyTorch as well. This shouldn't be a big deal, but the deep neural networks that I use throughout, they're pretty simple, right? They're dense neural networks, just 2 layers, a couple of hidden units, or nothing special. I would say it's not even at the core of what is done here. This is, I would say, the standard module that is plugged into all the agents. It's not about the deep learning itself. It's about everything else that is happening around it, right? So a couple of imports and parameterizations here. And now our agent, right? The agent takes as input the symbol, the feature with which it's supposed to work, the minimum accuracy, and the number of features here is set by default to 4. We have now the single elements that we have seen before on the slide, right? Epsilon in the beginning, 100% exploration. The agent doesn't know anything, so first the agent needs to explore. Epsilon decay is set to a value here close to 1, so that slowly over time the epsilon will decrease. But I define here a minimum threshold of 10%, so no matter how many episodes the agent is supposed to play, it will stick to 10% exploration even after many, many episodes. So the memory here is a DEC queue, that's like a queue, right? Where the maximum length is set to 2000. So after a certain point in time, the agent will have experienced well more than 2000 experiences, right? But the idea here is that when we restrict the memory to the last 2000 experiences, this is better because there's already some intelligence that was put in, right? The agent has learned already quite a bit, and we are not that much interested anymore in what the agent did in the beginning, right? It's like when you learn as a kid to play the game of chess, you might do some crazy stuff or some dumb moves, right? And later on, when you're much better, maybe an international master, for example, it might not be that interesting and relevant what you did as a kid at the age of 5. So that's the little motivation behind it. And a few more things I defined here. Gamma is set to a pretty low level here, not close to 1, but rather 50%. And yeah, a few more. The environment here, it's the one from before. And I was saying it already, the dense neural networks that I use throughout are pretty simple and straightforward. So just like 2 layers, and here you see the output layer has 2 values, right? And this is meant to represent either action 1 or action 0, right? And later on, the agent will choose then the one which has a higher value, right? So this is there was a question before in finance, right here. This modeling is just about the direction, right? Therefore, we just have 2 actions, right? The agent is supposed to learn how to predict the market in terms of just saying the market goes up or down. That's the prediction game, just 2 possible actions here. The ACT method here now embodies what I was explaining with regard to the exploration and exploitation, right? As long as the random number that is drawn is here below the epsilon level, a random action is chosen, and you know by now already that epsilon is decreasing over time, so this is less and less, and otherwise we make a prediction given the state, right? Then we get like two values for the two possible actions, and the agent chooses here the action, either market goes up or market goes down, where the value is highest, right? The argmax gives me here a 0 or a 1, right? And this is about the prediction, right? Then we have the replay. This is the part where the agent learns and updates the policy. Right? We have experiences after a certain point in time, and then the agent goes, reviews the experiences, and based on the experiences, updates the optimal policy. And over time, that's the idea, the optimal policy is getting better and better. Right? There is no guarantee, right? This is not necessarily going in a straightforward linear manner, right? This might getting better, might getting a little bit worse, might getting better, right? But overall, on average, you would expect the agent to learn in a way that the agent is able to play the game better and better, at least on average over time, right? And what is done here, you see it is the implementation of the algorithm that we have seen in terms of like a formula on the slide before, right? We have the current reward. We increase the current reward by the discounted delayed future reward, right? So this was the immediate reward plus the discounted delayed reward, the two of them together. And here, this is all for technical reasons. What you see here, that's the major step, right? This is then the point where we have the state, the target as calculated before. So here it's like a little bit of, again, technical stuff that's happening, and the agent updates based on a randomly sampled batch. Let's say, I think by default it's always set to 32, right? It does the replay based on a random sample of 32 experiences, and experience by experience, the model is updated, right? And here's the epsilon decay that is applied to epsilon after every round. Then we have the core method here, the learn method, where we play, I don't know, 100, 200, 1,000 episodes, right? This is to be defined here as the argument. We reset the environment. This is for technical reasons with regard to TensorFlow. We do a reshape here. Then the action is taken. Right? We know either it's exploration, so random action, or it's exploitation, where we rely on the optimal policy. Then we get, by stepping the environment one step forward, we get the next state, the reward. These are two Boolean values, right? Either true or false. Again, for technical reasons, we need to do the reshape here, and we append to the memory object the current experience. And this is repeated as often as possible, quote unquote, right? Either the end of the data set is reached, or I run into a breaking condition where done is set to true when I drop, or the agent drops below a certain minimum accuracy that we have defined before, but the agent plays as long as it is allowed to play, right? Until done is true, either at the end of the data set once again, or when some other condition is met. And if this one game, let's say, is finished here, then we do some housekeeping and a little bit of reporting, so printing out certain things so that we can follow along what the agent is doing. And last but not least, we have here the test method, where we're saying usually then you wouldn't go with the minimum accuracy defined, right? You can do, right? Here I set it 2.5, but you don't have to. Here it has a different meaning. We simply say, well, we are not interested. The way I've written it out here, we're not interested in any cases where the agent is better than coin flip, right? 50% is something that even the random agent from before is able to realize. So we want to expect something better. So therefore I said it here, but there is no need. We could also, for example, let's say comment this out, or rather set it here to 0. We could argue for that as well, so that we just observe what is happening there or not. So the functionality is similar to learning, but here is no exploration whatsoever. It only relies on the optimal policy. Right? This is just like, again, some grandmaster might be preparing for an important match against the old rival, right? And he might try to play different lines, as they say, right? Let's say in a certain popular opening, right? And this trying out, I think, ends when the real game starts. And this is the idea here as well. There is no exploration anymore. The agent is supposed to exploit its knowledge and what it has learned to the full extent, right? So that's the agent here. So let's see how it works in action. I have set the seeds. I have instantiated here the environment. I work with euro, yes, dollar. Log return as the feature. I set the minimum accuracy to 49.5%. And I say, give me 4 lags. So I could set this to 8 lags or 20 lags, but by default I work here with 4. And I mean, the reason being that in chapter 2 I introduced a card pull game from Gymnasium, and this has like 4 data points, right? So I have this here in line with what was introduced in the chapter before. So let the games begin, right? And you see here the agent is playing episode after episode. Some might be shorter, right? When the agent falls below the minimum accuracy level. Some might go until the very end. You see, it has reached already the end. This is the maximum amount. That's the length of the data set minus the number of lags. And here at the end, you see, oh, just 12. So this was early breaking. And now we can go and see what the agent has accomplished, has learned. And obviously it reaches an accuracy here of 52.5%, so better than just a coin flip, better than 50-50, and the total reward is the same. Why am I doing it here 5 times? Here to illustrate that in our setup here, we are just working with a single data set. Again, we are related to the question, or here this is related to the question before, right, where we needed to recognize that financial data is limited. Here we have 10 years worth of end of day data for euro, yes, dollar, and this is simply like 2,603, and the data doesn't change, right? So when I play it 5 times or play it 10 times or 500 times, it will always be the same result, because once the learning, the training is finished, the optimal policy is deterministic, right? It will do always the same thing when presented with the same numbers from before. So there is no random element anymore included, no exploration or whatnot. This is now just what the agent has learned, and it does the same trick over and over again. Right? We can now try and maybe let it learn a little bit more. And again, as I was saying before, this might now further improve the policy, but there is no guarantee whatsoever. Right? So the agent can, in between now, even show worse performance. But since it doesn't take that long, I thought we can let it run for another 250 episodes. And you see it in between there's 2,600, then 13 again, and this is always due to the exploration part, right? We can maybe check here. Yeah, towards the end it takes a little bit longer here as compared to the previous 250, because in the very beginning, epsilon is high, and it will always just draw a random number, right? And this is pretty fast as compared to everything else that is based on the dense neural network. So you see, even here, after a total of 500 episodes, we still have epsilon here at 28%. So here you see the agent's performance has deteriorated. So this is now pretty fast because it's always, and again, it doesn't change the policy here in the testing world, right? It is below the 50% testing threshold that I was requiring. Therefore, it stops pretty early here. So again, there's no guarantee that the agent improves with more training. We would only expect, on average, over time, that the agent's policy is getting better. Yeah.
Where are you splitting for train and test data set?
Here it's all in sample. This is all in sample.
It could be that it's testing on the same data that it's
Yeah, it's not could be. It is doing it. It is doing it. So here it's really like when you are faced with a single labyrinth, right? And once you know the way out, it's always the same way out, right? So that's nothing more. That's the introductory example here. We just have this one thing. And I was already mentioning the methods, and I want to show you the synthetic data generation after that, right? Because this is really the problem that we now have mentioned a couple of times. So financial data is limited, and remains limited. You just get, in terms of end of day, next Monday you get one more data point. On Tuesday you get one more, right? But overall it is and stays the same. You have just this one data set. And here in the book I don't go and do a train, validation, and testing data split, right? For example, in AI and finance I do this because I go more deeply with regard to one example, with regard to training an agent, testing an agent, then deploying an agent, right? Here I go the other way, and for the applications I use simulation and other approaches to increase the data set, right? So, speaking of data set, generated data. It's chapter 5 in the book, so I jumped over the simulation part, because I think simulation, at least for those who have a bit of finance background, is the standard mechanism, the standard numerical method. The first paper, as far as I know, which was published about Monte Carlo simulation as applied to finance, is from either 76 or 79, but at least it's from the 70s already, back in the days when basically no one has had a computer based on which you could implement a proper Monte Carlo simulation. But the ideas have been around since that while, so it's a well-established and widely used method. But generative adversarial networks, this is of course something that only in this century, and the last decade actually, was invented by Goodfellow and his co-authors. And it is one way of getting around the problem of limited data sets. So here I have a couple of standard imports and configurations once again. For what follows, I again use just TensorFlow, but for those who prefer PyTorch, I think this might be a pretty simple and straightforward task to do it. Again, I have it on my list to do it later on when everything else now is finished. Maybe to find someone who is willing to translate it to the PyTorch world. And the example with which I'm starting here is a deterministic example. This has nothing to do with financial data. It's just for illustration and introduction purposes here. I define just a cubic function, and this is monotonically increasing. That's the reason why I decided here on a cubic function and not maybe on a full, let's say, sine or cosine or whatever, right? For one reason, and you will see later on that I can sort the data more easily. And here I use the standard scalar, use fit transform to get the data in normalized fashion. So we see it here now visualized. We have the real data here, the cubic function, right? And given the normalization based on the standard scaler, what I did before manually, so to say, with subtracting the mean and dividing by the standard deviation to arrive at the first moments being 0 and 1. This is here done with the help of the standard scaler, right? And we see the dashed line which represents the normalized data. So this is a bit more narrow in terms of the range of numbers or the interval which is covered for the values between -2 and 2. So that's my sample data set, and the generative adversarial network here relies on two dense neural networks. The one is for the generator, which is supposed to generate the synthetic data, and the discriminator here is the one that is supposed to learn, should also improve over time, to distinguish between the real data and the synthetic data. And the idea is that the generator becomes over time, with more training, better and better, so that the discriminator is having a harder time distinguishing between the real and the synthetic data set. So the example that is used, and I like it, in the original paper, is about criminals who print counterfeit bills, right? And the police is supposed to distinguish between real dollar bills, let's say, and the counterfeit ones, right? And the criminals are getting obviously better and better over time, better technology, better printing machines, whatever. And the police is also getting better over time. So this is something where the two neural networks are supposed to be trained in a way that both are getting better over time. But in the end, it should be the case that the generator is able to generate, in our case later on, financial time series data in the form of returns that are, or the data sets that are statistically indistinguishable from the original time series data in the form of the underlying returns. You see again here, there's nothing really specific in terms of sophisticated architectures, pretty straightforward, just two hidden layers in both cases, activation functions being rectangular linear units, ReLU, right? And the sigmoid function here as the activation function for the output layer for the discriminator, because the discriminator should just say is real or is synthetic, right? 0 or 1. That's a classification problem, right? It's a real bill or it's a counterfeit 1, right? So that's the idea here. But you see it's pretty concise, pretty straightforward, 32 hidden units. In our case now, this is of course what is coming now related to the cubic function. In the GAN create GAN function, we set the trainability of the discriminator to false, so the discriminator is not to be trained here, right? The model here is composed of the two models that we have seen before. So we have again a sequential model where we add the generator first, then the discriminator, so that we have here the combination of both, right? In the end, they work closely together, right? With criminals and the police, this might not be the case that they sit in the same building, but here they are supposed to work closely together, and again to improve both of them over time, right? So I create the generator, I create the discriminator, and the GAN. I don't know what the optimizer. Didn't I import the legacy one? Yeah, this is something, the output that you have seen. This is something related to the Apple M1 machines, the output that you have seen. How it's called? It says it legacy. It's the other way around. It's optimizer's legacy. Right. again, this might not show up if you execute this on a Windows machine, but here on the M1s with the TensorFlow version I'm working, they're just saying the code would run, but here you can read it. It would be slower than the legacy implementation, which is optimized for the M1s, right? So I now have my random number generator, and the core of it is here in train models. So the first step is that based on a random number generator, here random numbers, normally distributed one with, so standard normally distributed numbers are created in terms of batch size. So 32, 500, whatever. Synthetic data is now created based on these random numbers, based on the noise, right? Given the prediction, and you see it already at this point, the generator is not yet trained, but it already starts spitting out synthetic data sets. In the beginning, they might be completely off and have nothing to do with the original one, but after training, this might improve over time. So here, I chose randomly with the batch size the real data points, right? Discriminator is trained on the batch here, real data with regard to the ones. So here, it knows what the real data is and the synthetic data as well. So the discriminator here is shown what is real and what is synthetic, right? And it's trained on that. And then the GAN overall, the network is, the generative network is also trained on the noise with regard to the ones here. Recall, the discriminator is not trained. This is where the generator here is updated and trained and improved. And this is then repeated over and over again, with again the idea that the generator is getting better and better at creating synthetic data, and the discriminator is also supposed to be getting better in distinguishing between the real and synthetic data sets, and overall, in the end, hopefully, we have indistinguishable synthetic data sets from the real ones. So this is now done. When I train it for, you see this is done here for 5,000 times. This might take a bit. I do only printouts every 1,000 epochs. So this takes a bit. And I return here the final real data set, randomly chosen, and the final synthetic one. So this might take a bit. It's taking longer than the training of our reinforcement learning agent. But I don't need to wait that long for it. Let me maybe stop it. After 2000, we can check here. Oh, it didn't. Sorry, it didn't finish. But let me do it here for maybe just 1,000, so that we get some data. Sorry about that one. Wanted to speed up things, but now we need to rerun it in order to get some data as input for the visualization. This might not be yet that good after 1,000, but of course we could run it again for another 1,000. So here it's just like a line plot. So this has not really a proper meaning, but it shows like the two data sets. Both of them obviously random ones. So the one here in red, that's the real data from the last batch. This is randomly sampled, right? And the other one is randomly generated, right? Hopefully in a way that, I don't know, when I have a look at it, I couldn't say whether this is the same generator behind it or not. But let's be it as it is, because I want to have another visualization which is a bit more meaningful. Right? So here I get several data sets created, right, and do the inverse transform. And here I have now 5 synthetic data sets, synth 00 to synth 04, right, with 500 data points, more than the 32 numbers from before. And we see here the mean value. We see the, let's say the 50 percentile values and the maximum values, and we can already compare. Right, this is the real data set, and these are the statistical numbers from the real data set. You see the mean is 0. So we would expect from the synthetic data sets that these values are also 0, or at least close to 0. Some are not really, like that one, but here would say minus 0.0054, right? This is already pretty close to 0. But when we now have a further look, let's jump maybe to the maximum value. You see the maximum value, for example, is much higher than 8, which would be the maximum from the real data set. Yeah.
Just to say, we've got about 10 minutes left. Just as a sort of. Also, I was just going to ask about how do you sort of model black swan events when kind of generating synthetic data?
Yeah, I don't know why, but I'm getting asked quite often when I give talks or workshops or whatever about basically the unpredictable, right? When I'm talking about, for example, the prediction game or algorithmic trading, you want to predict what is happening tomorrow, and people are, how do you predict unpredictable events? I say, you cannot predict them usually, right? You can, again, in finance, there's a long tradition with regard to Monte Carlo simulation that I was mentioning, and there, for example, you have things like jumps that you model in, right? A black swan event in the financial market usually is something bad, right? You might have black swans that are also pretty good, but what people usually understand with regard to a black swan is something unforeseeable, which has strong negative implications, consequences, right? Like a market crash, what we have seen beginning of COVID, right? We have had the last larger market crash, right? And with regard to Monte Carlo simulation, this is then where you would put in a jump component where you say, well, with a frequency of, let's say, once every 5 years, there might be a jump of a size, let's say 25%, 20%. This is the way you would, for example, address it there. But here, with regard to the approach that we are now discussing, the generator can only learn from the data set that I'm feeding it, right? So when my data set that I'm using, for example, has as part of it, let's say the crash from the beginning of the COVID period, right? Then it will internalize that as well. And it will, every once in a while, so to say, will generate synthetic data where such a crash situation will also materialize in the data, right? But in and of itself, when you say, well, I have something that we have never seen, right? And you have an approach where you train something on historical data, by definition, it cannot be included. You must maybe impose some other element, like I was saying, like a jump component or whatnot, which you then add to it, or something from the outside, where you say, well, from a risk management perspective, let's assume that every once in a while we might see something as bad as X, Y, that, for example, right? But it's always, it's important to get these things correct, because most of the time financial markets don't move that much, right? And if you're then with your predictions pretty correct, it doesn't really help you, right? You want to predict the large movements in a proper fashion. So here the data, to conclude, is not yet at the level where we would say that's exactly the same. What I'm doing here, I'm sorting the data set. I mentioned it before, I use the cubic function because it's monotonically increasing. So I can sort the data set now. And you see the blue dashed lines are the ones that are synthetically generated. So after 5,000 iterations, it would have taken a little bit longer. Obviously, this might be a bit better in terms of the numbers and in terms of the visualization. But you see, overall, this is not too bad once I've sorted the data. It's not perfect, but it's not supposed to be perfect. We wouldn't want to have something here that it's exactly what we have observed, because we have still random elements included in there. So it should be close to it, but not necessarily doesn't need to be exactly the same. So now the financial example. I was telling you before that I used the one data set that we have seen before throughout. Now I work here with the GLD one, and I take 2 years worth of data. So 2 times 252 days here is roughly 2 years worth of training data. right? And I calculate the log returns now. I do the same transformation as before with the help of the standard scalar, right? And I recreate now the generator, discriminator, and the GAN itself based on 24 hidden units. The learning rate is set to a relatively small level. And I'm now going maybe, I can do just 1,000 to get started with. And the idea is now we train it on the log returns, that the generator is later on in a position to create synthetic data in the form of synthetic log returns, where standard statistical tests would say, yeah, these two data sets are from the same source, right, from the same generating probability distribution, or in other words, that the conclusion is that the data sets are basically indistinguishable from a statistical point of view. So the generation here is with regard to 25 data sets, synthetic data sets. Right, let's have a look at the first 4 synthetic ones. The mean value here is pretty close to 0, right? The synthetic data set, so it's not exactly 0, although I did the standardization because I take just 2 times 252. These values are already pretty close to 0. They are more or less on equal footing, so when we go through it, this doesn't look too bad. Here the maximum is quite a bit higher than here, so we have the opposite situation from what we have seen before, and our picture will tell us a story now. So this picture now has already a bit of meaning, or more meaning than what we have seen before in this regard, because this kind of fever curve, I like to call it that way, is a typical illustration that you would use in financial context as well, where you simply plot the returns as a time series, and I would say, yeah, they look pretty similar, right? We see here higher peaks for the original time series data and some lower lows here, more or less on equal footing. But overall, I would say, yeah, well, they look pretty similar. And when I now plot more of them, again in a later on sorted fashion, here now in a histogram fashion, we see now with regard to the histogram that it's not yet perfect, obviously, right? There are some parts I would say, yeah, the overlay is pretty good, right? But overall here, it doesn't agree, right? Maybe 1,000 iterations that I did before are not enough, or have not been enough. When I now do the sorting, you see, that's remotely close, but for sure not exact, right? So probably we would need a bit more training here. The final visualization now shows these are the synthetically generated data sets. That's the average of the synthetically generated time series data sets, and that's the original time series. So you see, this is not even like in the interval of what was created. So when I want to make life more easy, but let me do maybe the training and then I make life easy and show you I do another 2,000 here. So another 2, but I can jump to the book and to the figures with the 5,000 here. You see, it's not that long, 1:45 for the 5,000 iterations. This looks pretty similar, but here, for example, you see the 2 histograms from before, but now after the 5,000 training iterations, where I would say they look already pretty similar. So the highs are pretty similar here, the peaks, right around that one. The tails almost are overlapping exactly, almost on the left-hand side, a bit better than on the right-hand side. The here now, this one synthetic data set and the real one, I would say that this agrees already pretty well as compared to what we have seen before in this sorted manner, right? And the synthetically created financial time series, or the log return series here, right, now are really around the original time series, right? The red one is the original series that we have here, right? And everything else is synthetically generated. And now, when I would plot that one, also blue dashed, right, I would say we couldn't recognize it anymore. So here, of course, since I have it thick and red, we see it immediately. Green is again the average of the other data sets. So this would quote unquote vanish, right? It wouldn't be like before, where we had this one line which goes down, 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 and it's not even in the interval of it, right? And with regard to the tests, I've now done 2,000, so a total of 3. This should look similar. We see now after 3,000 iterations, this looks already much better. Here also that chart looks more like we would expect it. I would like to have it. And the simulated ones here, again, are now much, much better around the red one. The red one is now not the outlier anymore in this chart, right? And here I was speaking a few times of the statistical indistinguishability. Is this a proper word? Of the statistical test that we can apply. And one such test is the Kolmogorov-Smirnov test, which basically addresses the exact question or problem that we have here, namely that we have two data sets, at least two data sets, right? Where the question is whether the data set is generated by the same distribution, right? We have two samples. This is typically the language, and the question is, are the two samples from the same distribution from a statistical point of view or not? Right? And this is what a test does here in a pretty standardized way. So here you see stats.ks test. That's the only thing that we need. We have the synthetic data set and the real data set. The real data set is always here the benchmark, obviously. But we have more synthetic data sets. We do again some sorting, and we see that basically all but one data set has a p-value of 0.05 and higher, meaning that from a statistical point of view, all but one data set is or are indistinguishable from the original data set. So this test cannot tell whether the one data set is generated synthetically or not, or the other one is the real one. So from a statistical point of view, they look the very same. And this was the very goal that we had, right? The generator being able, based on some noise, some random numbers that we feed to it, to generate log returns that are from a statistical point indistinguishable from the log returns of the original time series data. Yeah, I think we are already through with the time. Didn't reach everything, but I hope the stuff that we have covered has been well suited to give you an overview of these things. And in particular, this GAN approach here is not limited, obviously, to finance, right? You can apply this to many other fields, and we know all of this when we generate nice images with, I don't know, recently I started using Croc from Elon Musk on X.com or DALL-E or whatever the image generator is. That's more or less the same what we have been doing here, but of course in a very, very simplified version as compared to what the image GANs are able to do, and given their architecture as compared to the very simple setup that we have used here in this context. Yeah, we haven't covered everything, but I hope what we have covered gives you a good entry point, and you have the resources to go through with regard to the other applications with that background. This should all, and the access to the preprint of the book, this should all be then hopefully straightforward. Thank you, guys.
Well, thank you once again, very interesting, learned a lot there. So there is a lunch break now, obviously feel free to grab lunch. I'm sure you'll be happy to answer any questions.
Sure, I'm around, and 10 minutes from now, here we start the book signing over there. I don't know where it is.
It will be in this
We'll be here, yeah?
Yes. Yeah.
Okay,
So
didn't know that, so there will be. Yeah, I can sit there.
So back in this room in 10 minutes, there'll be a book signing, you can ask any questions then. And once again, thank you for the really interesting talk. Another round of applause, please.
Well, they're welcome.
And you can use the app to rate